automotive industry, typically in piston manufacturing and design industry. So most of my career was started in the piston industry, and also few tenure carries in the appliances industry. So mostly I'm a pure design and development and application engineering person who deals with the customer, with all the customers in India, like Tata Motors, Maruti Suzuki, Hyundai, Kia, Nissan, Escorts, Ashok Leyland, JCB. So I had a team of around 5 members who work in design, simulation, and application engineering. This is my quick background. So today I'll be presenting about the recent trends about the usage of non-ferrous alloys and how it impacts on the engine performance when it is used in alternate fuels. So more than that, we have seen gasoline and petrol and diesels used in these days, and nowadays, because of very tight emission norms, our government has forced us to go into this alternate fuels where we use CNG, ethanol, LPG, LNG, sometimes ammonia. Ammonia is not in market now, but still under research stage. And also the recent trend is the hydrogen fuel. So moving from diesel to petrol, there is a focus on going to a hydrogen fuel rather than jumping directly to electricity. People are now focusing on hydrogen engine development with most of the customers in India. You might be knowing they started working on this development, and once the infrastructure is readily available, then it will be rolled out completely in production. So how these fuels is going to affect the parts, mainly the engine parts, and how it will affect, and what kind of failure modes will come, and how these elements is going to act on this kind of failure modes. That is what a quick slides I'll be going through this webinar. So let me share my screen and switch off my video. Yeah. Please confirm that you see my screen.
Yes, sir. Visible, sir. Visible.
Visible, sir.
Thank you. Thank you very much. So, yes, I am from India Pistons Limited. It's been 3 years in this company. Previously working in the similar product at Male and Federal Mughal is Tenneco. So most of the time in piston industry with the design and development. So I spent most of the time in optimizing the dimension, ensuring the strength of the product with great support of my foundry, casting, and metallurgist team behind me. So about my group, India Pistons Limited, it is a part of amalgamation group. Everyone know that Mr. Govindarajan, he is our executive director and CEO of India Pistons Limited. I'm reporting to him. So he works in India Pistons Limited, and he is a board of directors of India Pistons Limited and IP Rings and other few group companies. So this amalgamation group was established in 1938. We have around 500 people in R&D and engineering division. So over 15,000 members, including all the workers and other unit members. We have around 50 factories throughout India. We have a collaboration with the global members. So we have new technologies and processes with a lot of patents on hand compared to the MNCs currently in India. So we are a diversified. We have a product portfolio with the different verticals, both in OEMs, in the part components, and also in the plantation and retail areas. So we have multi R&D centers across all the regions, especially in Chennai and also in Alvar and other regions. We also have distribution centers across the country. Our total turnover is around 2.9 billion, and the component turnover is around 200 million. So these are the companies and the history where we started. Most of the peoples may be knowing, and I will quickly go through it. Started in 1940s with Simpson Co. Limited They manufacture the diesel engines, and ourselves, India Pistons Limited, we manufacture engine piston, gudgeon pin, piston rings, and liners. And we have Addition and Co Limited, where they manufacture the cutting tool and machine tool accessories. Then later, we formed a bimetal bearing company. Of course, they manufacture thin wall bearings for the crankshaft and the conrod small end areas. So we also have an amalgamation Repco Group Limited. They manufacture clutch parts and flywheels. We also have a Shadlow India Limited. They manufacture crankshaft and forgings. And Amco batteries for the development of lead acid batteries. And we manufacture traffic. So they mainly produce tractors, and they have a lot of plants across India. And we also have another group company, IP Rings Limited. They manufacture steel piston rings, and they have a collaboration with NPR Japan. We have two companies making piston rings, one in India Pistons Limited, and another is India Piston Rings, which is around 40 kilometers from North Chennai. It is at Marimlai Nagar. So other companies, Amalgamation Value Clutch, they make clutch assemblies with the JV of Value Fans, and also Bearing Limited Daido. So with the automotive engine bearings, we have a collaboration with Daido Japan. And IPL Shah, JV with the Shah Development USA, which makes forging parts. And also in several services and retail areas, like Higginbotham, Staff Access, and other plantation and other corporate segments. So this is a quick JV about our current group companies. India Pistons Limited, we recently had a JV with Dongyang Pistons Korea, typically to manufacture pistons for the companies in Kia in Antapur, typically all the models of 1.5 liter engine segments. So we manufacture piston. We have a technical agreement with the Kia, and we started manufacturing engine pistons at our company, and started supplying the pistons to Kia in Antapur for all the Celtas and other 1.5 liter engine models. So the another group company is Amrup, which I told you that they wholly owned, and they make a flywheel and clutch assemblies, bimetal bearings, and as I told the IP rings, we have a joint venture of NPR Japan, and also the bimetal bearings, we have a quick collaboration with the Daido Metal. We have market presence in various segments across all the segments, from tractor, gensets, bi-wheeler, and also in defense, off-highways, and also in locomotives. These are our main customers. We supply to Mahindra, Simpson, Tafe, Sonalika, Bemel, of course, Kia, Royal Enfield. So most of the customers in India. So typically, these are the piston types what we manufacture inside our plant. These piston types are basically out of aluminum alloy. So we produce pistons out of aluminum alloy and supplied both for gasoline engines and also for diesel engines. So we have various diameters ranging from 70 to 190 mm. So we have different types of technologies in the piston in the aluminum itself. Aluminum alloy, like aluminum alloy is generally a known metal, known alloy used in the piston industry for lightweight reasons, also in higher strength to meet the customer durability targets. So we do design from the scratch in India Pistons Limited with our team in R&D, and also we manufacture the parts and provide it to customer for the validation and testing, and roll it out to production. So we have pistons with pure aluminum alloys running in production, and also with we have a hardened coating on first string groove, that where the piston first groove, we can see in this location we have an anodized groove on the piston. And then so for some customers, we insert a nickel ferrous iron ring carrier, which aids to withstand the heavy pressure on the piston. So we also manufacture the type of piston. And we also produce piston with a small annular open inside this piston, where we call it as a cooling gallery. So it reduces the piston temperature, where typically used in truck of heavy tonnages, more than 40 tons, and also for the vehicles which we currently use in Mahindra and Tata Motors. So all these segments comes with the very high loaded engines which requires a cooling gallery for the piston. So with all types of crushings coming from all the divisions of the worlds and political leaders, forcing us to go for a tighter emission because of the world says that only the automotive vehicles produce lot of pollutions than any other industry. So automotive segments and other people have started focusing on reducing the emission norms and typically on NOx, PM from Euro 4, 5, 6, and now going to Euro 7 today. So with these stringent emission norms coming in, and we are looking for a lot of improvements in the material coating and all these segments. Typically in the aluminum alloy, we were very much focused on improving the fatigue strength and corrosion resistant materials with the improvements or with the combination of all the alloys by modifying the structures and other things. We are very much focusing on the aluminum alloys and other areas. Of course, more on the passenger cars and heavy duty trucks, and also the agriculture norms also is becoming tighter as it becomes a very typical area where the farmers in the agriculture industry face a lot of problems with relation to emission part, because all these emission smokes cannot be too lenient, as it may have impact on the crops, which will affect directly the agriculture part. Today, currently in tractor segment, we are working on TREM 3 and TREM 4 areas. The government is started focusing on TREM 5 segments also, which the implementation is getting delayed for another 1.5 years. So with all these emission norms focusing too much on reduction of the emissions, typically NOx, PM, CO, and PN also, particular number. So the scope for improvement of norms with the gas, petrol, and diesel is become very difficult. So with adding all the after treatments, DPF, SCR, still there are a lot of challenges to meet the emission norms, and the government has come up with an options of going with the alternate fuels. So the alternate fuels are more beyond like gasoline and diesel. We have LPG, CNG. These things are normally seen in our vehicles in day-to-day roads, and now the new thing is coming is the LNG, and of course ethanol is also one fuel which is in the talk of the news. They wanted to introduce this ethanol 20% directly into this petrol, and how it is going to affect our vehicle is a big panic to us. And so apart from that, methanol is another fuel which is still under research and not in production, but not in India. Now, of course, as I said, hydrogen is the one where they are focusing to introduce for the IC engines, which will typically give an output of water vapor as output, not either smoke or something. The water will come out of the silencer. You can see, you would have seen in the YouTubes or other Western countries, and where Toyota, Cummins, and more JCB and most of the customers have started introducing across the areas. In India, of course, most of our truck manufacturers, they started showcasing their hydrogen engine based vehicles. And now recently in a vehicle rolled out in Pune with the use of hydrogen fuel cells also. Of course, the usage of electricity, battery, and other things still is at the beginning stage, and trying to take over all the IC engines, and still being an IC engine supporter, and with the help of gasoline, diesel, and other alternate fuels, we are trying to improve the parts design and material properties to cater the needs of this the technology. So with this, having this alternative fuel, so we have a lot of challenges here compared to the gasoline and diesel. Just a moment. So if you see that, of course, gasoline, diesel, it has a lot of hydrocarbons and it can emit a lot of soot, or you can, as a layman term, it's a smoke, black smoke coming out of the vehicle. So in order to avoid all these challenges, the carbon content is greatly reduced in combustion natural gas and also in the LNG and other ethanol and methanol. As you can see, hydrogen, you don't have carbon, it's just hydrogen. And it interacts with the air and produces water vapor. But the other challenges, what the engine industries or the fuel industry sees is the energy content, that is the calorific value of the fuel. When you see compared to gasoline or diesel, the calorific value of LPG or CNG, LPG, and if you take hydrogen, okay, I will come to hydrogen later. So it will be little bit higher compared to gasoline and diesel. So what it means, it emits a lot of heat inside the engine compared to gasoline and diesel. So the lot of heat on the piston, a lot of heat on the reciprocating parts, engine valves, a lot of heat released across the engine block. So we need a lot of new technologies, new coolant type of grades, and we need very low viscosity oils, because the more amount of heat will definitely will make the oil viscosity to be very harder over a period of time because of their very high heat content. It's a basic, like you put more oil in your pan in the kitchen and you heat it for some time, it will become very hard. So that kind of situation may come. So the industries have started focusing on a very thin oil viscosity, all those things. So when these more amount of heat comes on my part, typically on the piston, I'm subjected to different kinds of thermal and mechanical loadings. Typically on because I am the first phase of the like the piston is the first part to typically face the combustion byproduct which is produced inside the cylinder. So it will be too much amount of NOx. The particulate matter is the oil which is coming from the sump. So and also the hydrocarbon emissions, and also the carbon monoxide and carbon dioxide. So all these emissions will have a major role from the piston and piston ring parts. So when these pistons are subjected to these kind of heat and thermal loads, and also to meet the tighter emissions, so I need to focus more on the material where I need to withstand this kind of heat. So I will talk about this material strategy and how it is going to affect this performance on how to meet the durability and the emission targets. So all this CNG, LNG, and of course ethanol, the most of their outputs will be like water, and they produce a lot of corrosions, like pitting marks on the parts. So that will be very dangerous, and it can create a fatigue kind of a failure over a period of time, which we do not expect on a critical part out of an cylinder components running inside the engine. So in order to avoid all this kind of corrosion related issues and thermal related issues, we have already have a solution of an aluminum alloy with a higher wear resistant and corrosion resistant material. So beyond this ethanol and methanol, we have a lot of challenges with respect to hydrogen, with respect to material. Of course, a lot of studies and papers coming out of hydrogen, and results say that this energy content, it almost releases energy content almost 50% more than this regular methanol and ethanol, and it has a very high heat release rate. It is like think of a rocket burning this fuel, and you need more amount of coolant or water to splash it so that we don't have any damage. This kind of a situation is coming out of hydrogen condition. So we have a lot of heat thermal release rate is very quick, and this amount of impact on the material like aluminum alloy or on the piston on the cast iron on the liners or the wall guides, which has a different materials like titanium and other portions where it's subjected to combustion products. And also this hydrogen output is nothing but byproduct is water. So even the traces of water will be available in the intake manifold and also in the cylinder heads and also sometimes in the exhaust. It will leaks down and it will go sometimes and get trapped inside the piston and other areas, which over a period of time will start making a corrosion kind of an effect. So these kind of a corrosion effect will definitely affect, will make a kind of an pitting marks on the aluminum alloy parts, and the hydrogen will start getting diffused into the spitting marks, and it will completely collapse the microstructure. What we see in a regular aluminum alloy, and an aluminum alloy will have a normal microstructure with a very coarse structure of silicon particles and other with a 50 microns to 100 microns range. So there will be an intermetallic phases will be there, and with these small kind of a pitting marks, the hydrogen gases can easily get entrapped, and it will make a fatigue kind of a problem. Like it will generate a crack, and it will completely make the piston to break over a period of time. So to avoid all those things, this microstructure on the aluminum alloy plays a major role, and its heat treatment and its finer grain structures. So all these things are important, which plays a major role in the material development. So though I am in a design industry, more focusing on the design perspective and the strength point of view and a weight point of view, the microstructure and the material point of view is very important to cater the needs of this design, whatever we provide. Of course, 60% comes out of a design, and another 40% is out of the material. So with these alternate fuels and having its properties, which is making the engine parts to destroy the regular reliability and the function of the engine. So how we are going to cater this, we can see in the upcoming slides. I'm sorry. Okay, as I said, these alternate fuels are very much dangerous because it is not that they don't have a higher carbon content, because of lesser carbon content and more amount of hydrogen coming in. So this more amount of hydrogen and also with oxygen, more and of course the air does not contains oxygen. It has nitrogen, other gases coming inside. So it creates a lot of NOx, of course CO and other things, which will have a lot of abrasive wear and adhesive wears created on the parts. You can see that the CNG, ethanol, LPG, all this will have a similar kind of calorific value with a lot of the heats, and the outlet will be, most of the things will be water vapor and water coming in. So this water and water vapor will destroy the oil viscosity, and it will make the aluminum alloy to wear over a period of time. You can see the wear is something like, it will not be flat. It will become an like a curve-shaped structure. This kind of an wear, which is seriously not allowed or not advisable over a period of time, or it creates a problem within a short span of time, affecting the engine performance. Like in a layman term, that you need to replace or you need to top up your oil again and again. You top up your oil, for example, for 1,000 kilometers, you are topping, you have an oil of 1 liter. And if you have this kind of an abrasive wear, definitely you need to pour more, another 2 liter of oil, which customer will get fed up. So in order to avoid all those abrasive wears, and also because of the very high heat release, the friction between the parts, like in piston, of course, it is a reciprocating part going up and down. So it is carried over by the piston ring. So the piston ring and piston goes into one portion when it is subjected to heavy thermal loading produced out of this combustion byproduct. It creates a lot of friction in between these parts, because the oil which is supposed to guide the piston rings and piston inside the with the friction, like some amount of friction should be there. It's a kind of a hydrodynamic or mixed lubrication is supposed to be there, but it is not. It is a dry lubrication. So because of this dry lubrication, the piston is getting eroded, and a lot of aluminum particles get sticked on the piston rings. That we call it as an adhesive here. So to avoid this, of course, we have materials which we can explain in the coming portion. Of course, I told you about the hydrogen, quick sketches about a normal intermetallic phases of our microstructure, and because having a very high hydrogen fuel pressure release and heat release rate, there are chances of pitting marks created on the parts, which can slightly make your aluminum alloy brittle, and aluminum alloy becoming brittle is very rare to see this kind of a phenomena. And this slight brittleness will open that intermetallic phases and allow the hydrogen freely go inside it and create a kind of an embrittlement situation, which makes a fatigue crack over a period of time, which is not a good scenario for an aluminum alloy with the piston running in an engine. So about the piston aluminum alloys, of course, we have different grades of alloy. I did not disclose my material name here. So focusing, we had a low-grade alloy those days used in Euro 3, Euro 2 emission norms, where the engine power density did not call for any high power, high torque conditions in passenger car, diesel and petrol engines. Of course, in the Maruti 800 and other small engines, did not call for a very high material required. So we started with going with a normal etotic alloy, which has an 11 to 13% silicon with nickel content of 0.7 to 1.3, and going to a copper magnesium. So with these characters, we try to manage with the upcoming emission norms, but the upcoming emission norms started asking a lot of reduction in their parameters with respect to PM and NOx. So all these things has influence with respect to the piston material. So the piston material like silicon, copper plays a major role. And when the power density increases in the engine, because to meet that tighter emission norms, when the cylinder pressure and heat release rate started increasing, we went to this medium grade alloy, which asked for a copper percentage of 2.5 to 4 and with a higher nickel content. So we saw them good improvement in wear resistant and also good improvement in the fatigue strength also. And more than that, when these kind of an aluminum alloys or like medium grade aluminum alloys started using in the passenger car, diesel and truck industries, and even like locomotive industries, they started asking for a very high fatigue strength. And we started focusing on the high grade material alloys with more higher copper content. So this help us to make the fatigue strength more higher compared to a base one, almost 40% at higher temperatures. Because the temperatures on inside the byproducts of combustion, typically it is 1200 to 1500 degrees centigrade, and it will change according to the fuel, gasoline and diesel and other alternate fuels. So having all this thermal loading conditions and other things, the requirement of increased percentage of copper content and nickel content plays a major role in improving the fatigue strength of the material at higher temperatures. Typically, these kind of higher temperatures of more than 350 degrees seen in the piston, typically on the piston, I say, it is more seen on the piston side. Because it cannot be more than 350 degrees on a diesel piston. Typically, more amount of heat, obviously, the melting point starts for the aluminum alloy. The aluminum alloy melting point is almost it starts with 500 degrees, but the recommendation for maintaining the fatigue strength or the durability of the parts, it will be strictly below 400 degrees centigrade. So there will not be any part allowed to run with more than 400 degrees on the piston with any kind of an alternate fuel. So we had a high grade alloy with a lot of elements getting improved, and which gave a better strength, fatigue strength at elevated temperatures. It's in a basic chromium elements and its properties. I'm not enough metallurgy expert, and I have little steps gone through about each elements and its function, how it helps in reducing or improving the wear resistant and thermal expansion and fatigue strength of the material. Of course, in aluminum alloys, we have seen different kind of alloys used for long endurance parts, and also for the high horse, I mean like a race car pistons. We normally use an eclectic piston alloys for a normal durability engines, wherein we wanted to cover a 50,000 kilometers mileage, and we do not use this kind of pistons for hypercritic alloys because it has a very good support in terms of reducing the thermal expansion, but it is a little bit of brittle in nature. So these kind of hypercritic alloys are typically used in loaded conditions where like in smaller gensets or in compressors. This is where the applications where this hypercritic alloy is used, because the brittleness of the material will make the parts to break over a period of time if it is used in high durability parts. So these kind of alloys typically plays a major role. These alloys can be either casted and forged. Of course, the difference between the cast and forged, the cast one will have a very good strength, which typically meets a customer requirement of having a good warranty target. But when you go for a forged, wherein the big two-wheeler pistons and also the force race car pistons, where it is running for more than 9,000 RPM and 10,000 RPM in engine, so it can sustain only one time. So the life of the part is very less. So we cannot have a cast type of an aluminum alloy parts in those cases, and we prefer to go for a forged piston. The forged piston, obviously, it is a tightly packed process. It is pressed by an die and other things coming from the like the hot dies at a temperature, and it makes the microstructure very compact and increases the fatigue strength better than the cast. So not all the time that we can use the forged one, because it has some constraint in making the complicated microstructures, but which the cast parts can be done in the gravity die castings. So when we started focusing on this hydrogen engine development, where the very high heat release was happening inside, and we see a lot of technologies coming up. In our case, as I told, that we also manufacture a very high-end technology of pistons, which should reduce the temperature of the piston and try to maintain a good amount of element percentage to meet the customer target. And still beyond that, this fuel like hydrogen will demolish this piston in a very easy way, like making a pit, like as I said, that there's a pitting mark, corrosion marks getting created, and it will spoil the complete the microstructure of the part. So what the current trend is going on today is like a normal aluminum alloy casted with the gravity casting will have a very coarser microstructure. You can see here with the silicon particles spread across. And typically, when you see on the left-hand side here, the piston as a part is subjected to very high thermal load. And this is the portion, we call it as bowl rim region, where it is subjected to very high thermal load and mechanical load. This part is very quickly prone to a fatigue crack. So in order to avoid this kind of issues in an alternate fuels like when we are using hydrogen, beyond despite the hydrogen has a high thermal release rate, we use a technology called cooling gallery inside. You can see a small hole inside, and even though it reduces the heat on the bowl rim, beyond that, because of the high heat release rate and its impact on the part, create a lot of damages and creates a fatigue crack on the mountain area. So in order to cater this requirement, there is a process named. There are a lot of names and a lot of competitors has, and I will say that microstructure is modified typically on the ball rim region in the casting stage itself. So when it is a kind of a melting process, there is no like added alloy or something done along with this melting process. It's only refinement of the microstructure with the building. Like it is a kind of an welding process, but not. It's a kind of an melting. The melting is done in a way that microstructure is optimized and made finer. You can see in the right hand side of the photo between the coarser and finer structure. This kind of a finer structure will be very helpful and it will make the silicon particles very much reduced, and it reduces the intermetallic faces gaps, and it improves the finer grain sizes, and very helpful in reducing this kind of cracks. You can see the some analysis says that there's a difference of grain structure between this modified microstructure and also a normal coastal microstructure. So this kind of technologies with an modification in the casting structure are nowadays used by all the customers because even in hydrogen engine, despite they have an naturally aspirated engines and also with the turbo fitted, a lot of challenges faced the customer and like knocking and all those things. Knocking is very detrimental to the parts, which can damage it despite you have a very high technology and a very sensitive material. So not all cater all those needs, and then we need to have this kind of high technology like a modification of the microstructure and other things. Some competitors will do modification with the help of a welding process, and some will get optimized in the casting portion also. So all those things will definitely aid in meeting the engine performance parts, and thereby not affecting the durability of the parts over a period of time. Of course, quick takeaway from this meeting, despite we have a lot of challenges coming in, ethanol coming in our day-to-day vehicle, CNG where we use in our daily cars, and hydrogen which may come in the future for these truck applications. Of course, there are hydrogen fuels used in IC engines and also in fuel cells. So all those things, when you come into the picture, more than the design, the material plays a major role, and having a very improved fatigue strength and high corrosion resistant and high wear resistant material definitely will reduce the risk and will meet the customer target and to not to use this kind of an alternate fuels, and also to reduce the emission norms. Of course, we also use this some amount of low hydrogen. We have a hydrogen content running inside the casting process, and we use proper heat treatment. So we are trying to ensure that the low hydrogen content to be used in the casting process, and this will help. This will be helpful, and also to minimize the porosity levels. Generally, this Pistons parts produced out of gravity die castings, we have challenges in creating a lot of defects and reducing the strength of the parts. Despite we allow this kind of defects in very traditional and conventional diesel and petrol engines, which we do not expect this kind of defects to be prone to any kind of issues in the hydrogen engines, which is very severe in terms of piston breakage. So we are trying to reduce the porosity level and the casting levels in the and enhancing the strength in the part. Beyond this materials and other alloys, we also have an coatings coming on the piston part, wherein the direct, of course, some kind of an aluminum alloys may require a new technology, which some customers may not pay, and with the different kind of coatings on the piston crown portion, like a thermal barrier coating, will definitely act as a very good barrier against the hydrogen penetration. Because these kind of coatings will not create more kind of defects, and this will ensure that our hydrogen does not pass through these intermetallic phases and reduce the thermal mechanical cracks. More beyond that, it lies with the engine optimization and engine combustion area, where the hydrogen engine has a lot of challenges with respect to the knocking and excessive brake firing issues. Beyond that, as a supplier and as a manufacturer of using aluminum alloys, we have a lot of challenges in refining the grain size and controlling the distribution of silicon particles, because more amount of silicon particles is also very dangerous in terms of durability of the parts and other things. So the matrix and grain fine structure and other reduction of casting defects will definitely helpful to reduce the wear and other fatigue related issues in the parts. Thank you.
Do we have any questions from the audience?
Yes, sir. Can we ask?
Yeah,
Yes,
please go ahead.
Good evening.
Please tell your name and just go ahead.
This is Bhagiratham from Minix. Mr. Sathish, your presentation was absolutely good.
Thank you.
We have gone through your presentation. I just have a few queries because you are in the design department.
Yes, sir.
And you have been designing this component piston, so-called. And when you do an initial design of the piston, you will do separately for a gasoline piston and a hydrogen piston, or you will do as a piston as it is. When you do any analysis, magma analysis, जो भी आप design में tools use करेंगे,
okay.
These tools, do you use separately for a hydrogen piston and a gasoline piston?
Okay, if you talk about the casting simulation tool, it will be common.
So casting simulation tool is common for both.
Common for any application, because casting simulation tool, we are going to find out the solidification time, what is the flow rate of the molten metal, where the defects is formed. As you rightly said, of course, it is very important because the porosity level or the defects formed on the
stress concentration.
That is very important. So the magma or any casting simulation tool will be very helpful. For example, I allow around 0.5 microns of defect on a gasoline piston. Piston where I use it for gasoline engine. If I use it the same hydrogen engine, I will not allow any defects in that zone. So I have to be careful in deciding the defect formation on that parts.
Yes, stress zone hai na.
Yes,
for different material, the stress zone will vary. So you have to focus on the stress zone. Similarly, the ball rim that you are doing, do you do any test after the casting is done, after the machining is done on the ball rim?
See, after machining is done on the ball rim, it is a normal, to ensure the strength of the part, it is typically checked only in engine testing. Okay, so the engine testing is the final location. Beyond, if you ask me before engine testing, despite if we have a similar testing like UTS and other things, the hardness measurement, all things comes into picture. When it is subjected to deformation, thermomechanical loading, the engine testing is the right place where it tells us the exact failure mode.
No, I'm asking about the ball rim test, which you have shown in the figure, the crack that you have observed, which the ball rim and the crown area, you are susceptible for a severe crack at that zone. Exactly. Do you have any checking mechanism?
Have a hot and cold test, making the piston to, we heat the piston for some temperature around 300 to 350 degrees for some time and cool it immediately after some time. So this kind of variation in the heat and cooling will definitely find out this kind of a crack. So this is a basic test. We do it before, but what customer nowadays is asking, like as I said, that hydrogen going inside, hydrogen kind of testing in the rig is very difficult. So the engine testing is always advisable.
Excuse me. See, sorry to interrupt. We have exactly another minute more, so it will be our team's meeting has a time limit, so it will be over by another 1 minute. 3:30.
Okay. The last question. Refining
Yes,
of
yes.
the
No,
microstructure.
If you have further questions, we can rejoin. That's what I mean.
Okay,
Yeah,
we can
if you,
rejoin.
if you, yeah,
Okay.
within a minute.
And let us refine that.
Yeah.
Yeah.
If you want to have more questions, then we can rejoin in a minute once the teams will get automatically
Let
signing
me
off.
see if
Yeah.
I can finish it. See, regarding the microstructure,
Yes.
the focus is more on the microstructure. How is the inoculation or how is the treatment that you are doing for the microstructure in the casting section?
See, we have a normal T5 heat treatment process.
No. This I'm not talking about heat treatment process. I'm talking about the mic. I was just asking the microstructure के लिए we do either tie-ball wire addition or tablet addition. This is being done in the casting area. Is it being added in the metal that you are pouring into the mold?
Okay. I'm not a process expert also. I'm sorry to say that. But definitely the casting process, whatever we do it in our regular production, all this degassing by a rotary stirring option is done. I not avoid.
No, sir. No, Mr. Satish. It's not about degassing at all. It's about the addition of tie-ball into your metal to improve the microstructure. Okay. Maybe you can check up with your team just for this thing. We have wire feeder attachments where you can feed the wire, this tie-ball wire, at a particular length into the casting along with the metal that poured into the mold. And this crown, the crown area, which is very, very highly susceptible for crack, in hydrogen piston, are you making any changes in this crown with respect to gasoline crown, or you're making it thinner, or any changes in the design?
Okay, this is the design perspective point of view. In order to reduce this kind of cracks beyond this microstructure, the improvement in the increase in the radius will also be very helpful because very thinner radius can be subjected to like a quicker crack formation.
Okay, Satish, the last question is, I don't know whether you know this or not, but you can ask your people. Your crown formation is at the bottom or at the top? When you cast the casting, your crown is at the bottom or your crown is at the top?
Crown is at the top.
Top. So
yes,
you are susceptible for higher oxide formation on the crown. Am I right?
Yeah, we have this riser coming up.
Riser coming up, but in fact, okay. So you are doing anything to reduce those oxides there?
The riser design plays a major role. And also the turbulence of the material from the gate side also plays a major role. The addition of stocks at the crown level, whatever we maintain at this junction, of course, before pouring the casting, we do in the simulation tool and we'll ensure the riser design also is optimized in order to avoid this kind of thing.
Okay, you are using copper 3 to 4%.
Yes.
So what exactly, how it helps in corrosion resistance, or how it is helping us?
Okay, this is based on the trial and error done in the past with our predecessors. With these copper and added with the copper improvement, we saw a good strength. Like it played a major role in this.
Okay. Okay. Satish, this particular this hydrogen we were talking about, huh?
Yes.
This particular thing, is it going to be the future of this one? We are going to design the piston with respect to the hydrogen fuel, or we are going to still continue with the diesel?
No, the hydrogen, it takes some more time because of the infrastructure development is less. But with respect to development of the piston material and technology, it is still under research. Like not be same as what we see in the regular diesel.
Okay.
Like I'm sorry, I forgot to ask you about your background.
No, basically I'm a mechanical engineer only. For the past 30 years, I've been working in various foundries, and I'm heading Minix Metallurgicals. We supply master alloys to various casting industries.
Okay.
So we are well versed with these master alloys and all these particular microstructural information. So that is why I am asking you all these questions.
Okay, so thanks. Thanks for asking. Yeah.
And last question, do we anyhow, because you are a manufacturer of piston for so many years, you have been into this particular field. This particular port for testing, do we do for any of this metal that we use? Port for it's a inclusion test, actually oxide test that we do.
Yes, sir. I mean, there should be some tests done inside my team. Maybe I'm not able to answer your question. I'm sure that to reduce all these kind of defects, whatever the elements added, or whatever the parts which you told that should be done to improve this casting process.
Sathish. Okay, thank you very much, Sathish.
Thank you, sir. Thank you.
I see a few more questions in the chat box. Okay, so somebody has given how much density is better to reduce the pinhole and gas holes? How much density is better to avoid pinhole and gas holes? Yeah, maybe that will be the last question to answer.
I have a genuine answer here because I don't have an answer for this point. Sorry.
Okay.
Hello, can I talk?
Yes.
Sathish.
Yes.
Hello?
Yes, I can hear you.
Yeah. Basically, to answer of that question is, in case of density index, if they maintain less than 1, in that case, the pinhole issue will be eliminated. Okay, so have to check the density of that metal, molten metal.
The density index for any high combustion engine is maximum 0.5, sir. If we target 0.5, our piston, our component will be absolutely fine.
Right. That they will require to test by using that density index method. That is the method to use take the density. Okay. I have one question for you, Sathish ji.
Yes,
whether you are using any plant for vanadium or zirconium to improve the corrosion resistance and to form intermetallic precipitate that inhibits recovery and recrystallization, because that is the major concern in the piston.
Sir, no. The major elements, it will not come into the major elements. But I will also check whether the traces are available.
Yes, I can reply to this one. Actually, all the high-end engines nowadays, we are using vanadium and beryllium together.
Okay.
Although we don't spell out this particular thing to our customers, but vanadium and beryllium together will really help in reducing and improving the properties of the casting. So although vanadium is very difficult to store, but still, if you can have a good storage and you can use vanadium along with beryllium, the alloy will be much better and you will get better results with such an alloy.
Okay, thank you.
Thank you.
Okay, then.
I have query.
Yes.
Yeah.
Hello,
One last question to go.
Yes, please.
I'm Pallavi Deshmukh from Minex. I just wanted to ask you, I have seen some 4 allied elements you are adding in the slide number 12, that is copper, magnesium, silicon, and nickel. So how you are adding all these elements, whether in the form of in a master alloy or as a pure metal?
You know, what you said is like, how do we add these elements?
Yes, whether in the form of in a master alloy or as a pure metal.
Madam, we generally get it as ingot in our case. We don't prepare alloy. So,
There must be in the form of master alloy, aluminum, copper, aluminum, magnesium. Is it so?
Yes, it is. Master is available.
Master available, right?
Yes.
Also
Okay,
for the-
then
Yes,
there
please.
are many questions, sir. Sir, how you are achieving the you take the silicon modification? In slide number 14. Slide number 14 is there. Because the silicon percent is very high, that is up to 30%. So it should get modified because it's a long brittle nature of the detected silicon will affect the mechanical property of the pistons.
Silicon, yes, of course, it has a major impact to reduce the ductility also. So that is why we, in our regular passenger car engines, we really don't use this hyperetetic alloys.
Yes, because you have to break this long brittle nature of the eutectic silicon phases into a small fiber structure by adding strontium.
Exactly.
So generally, strontium is added to improve the mechanical properties.
Yes.
Are you adding?
Ma'am, we add strontium, yes.
Hello, ma'am. I will give answer to your question.
Yes, please.
Yeah, basically strontium is added to modify the silicon. Okay.
Yes.
The Al4S. Hello.
Yes. Al4SR.
Al4SR phase which is formed now that completely cover the silicon and avoids the growth of the silicon. Just like of that in case of HGIN, the carbon get global form. That in case of that eutectic alloy, silicon converted into global form, and the needle point or stress laser points get completely eliminated by using the strontium.
Yes, that's the mechanism.
Yeah, right.
Thank you.
okay, thank you everyone for joining this webinar, national webinar on non-ferrous. Yeah, I really thank the Southern region and the Chennai chapter joined together. We had this wonderful day, Saturday afternoon. I really thank Mr. Sathish Babu, Head of R&D, India Pistons Limited, for this wonderful presentation. And I thank each and everyone who joined this meeting. I really thank the Chairman, National IAF, Prabhu Sen, and Mr. Palli Murugan, Southern Region Chairman, and N. Prabhakaran, Chairman, Non-Ferrous, Southern Region, and K.S. Anbuchelvan, Co-Chairman, National Non-Ferrous Committee, and Ramesh Babu, Honorary Secretary, IAF, Southern Region, and finally, Bakul Shah, Honorary Secretary, Non-Ferrous Committee. I wish a happy weekend for each and everyone, and good to see you again in another webinar. Thank you.
Thank you very much.
Thank you, sir. Thank you.
This single connect.